I'm Major Selena Fletcher, and welcome to the Multi-Agent Unmanned Aerial Vehicle Systems, a Systems Analysis Brief. I'm going to tell you a little bit about myself, and then I'll go ahead and dive into the brief. So I've been in the military for about 20 plus years. I've done reserve time, and I was also in the enlisted side prior to me switching over to the officer corps. I decided to switch over because I wanted to use my passion of math and love of research, kind of roll them into one. So I became an Operations Research Systems Analysis, which is we call ORSYS for short, in 2018. I have an undergrad in computer science, and I have a graduate degree in computational science that I got from Georgia Southern in 2018. So we're going to move right on into the brief. So the purpose of this brief is going to show you some of the results that I received when I did my regression analysis as well as my parametric analysis. Oops, excuse me. Let's dismiss all of those so they don't pop up no more. All right. That I conducted on the outputs of the simulation that ARL, which is the Army Research Laboratory West, had built. We'll go over the background a little bit, then we'll go over the methodology we use, and then I'll show you one of the regression analysis results. So in today's modern Army, it's important for us to modernize how we execute missions by using advanced technologies. And one of those technologies is unmanned aerial vehicles. Since this technology is becoming so commonplace, we can now deploy them at scale. So what we want to do is be able to now learn and kind of understand how does adding UAVs plus human operators with different types of mission sets. So the Combat Capabilities Development Command Army Research Laboratory, they have a West location that's down in Los Angeles. They created a reconnaissance mission simulation consisting of humans and UAVs. The UAVs that are simulated in the simulation, they're an abstract representation of quadcopters, flapping wings, as well as fixed wings. So what we want to be able to do is we want to explore the trade space in order to understand how does adding UAVs into a reconnaissance mixture, how does that enhance the operation? So we have some performance outputs. We have accuracy, timeliness or speed, and then operational signature, which is also, we could refer to that as noise level or noise decibels. Kind of a little interchangeable with that terminology. So we want to know how does these different asset mixes impact the reconnaissance operation. So to understand this, what we did was we developed a full factorial DOE that allowed us to explore every combination of all of our factor levels. And our factor levels were 0 to 10 for humans and fixed wings, and 1 to 10 for flapping wing, as well as quadcopters. We did a full factorial because we wanted to know each individual combination and how does those combinations affect the outcome on those performance outputs. And the ultimate goal is to develop an application that will allow a senior leader or a decision maker to interact with it, to weigh different attributes and see what is the optimal mixture based off of those attribute weights that the senior leader put in. So if there's any questions. Okay. So here is the methodology that we followed to develop the DOE in our Shiny application. As you can see, it's a 6-step methodology. In the first phase, we did a little problem scoping, and this is where we worked with our sponsor to understand what their needs were, what they wanted the application to do, all the different features they wanted the application to have, as well as conducting our literature review so we can determine which multi-attribute decision-making technique we wanted to utilize. And as a result of that literature review, we utilized a simple additive weighting technique because it was the most basic and it was very easy to implement and understand how to weigh the attributes. And because we have so many attributes, we didn't have to worry about them equaling up to be one. They can weigh them based on how they valued each attribute. And the next steps 2, 3, and 4, we developed that full factorial DOE that I mentioned before. Since we wanted to look at every factor combination, our DOE ended up being 12,000 rows. And that allowed us to look at every combination of our 4 factors, which is those 3 UAVs and our human operators. The one thing we had to ensure in our DOE is that there was no rows where there was a combination of 0 quadcopters and a combination of 0 flapping wings. And that's because for the simulation, you always had to have 1 quadcopter or 1 flapping wing present. And let me backtrack. Now that I'm saying that out loud, I misspoke before. Our human operators and our fixed wings had to be 1 to 10, and our flapping wing and our quadcopters ranged from 0 to 10. So now that part makes sense. I just realized that I kind of misspoke before. So after we developed that full factorial DOE, we then developed what's called a wrapper function. And what the wrapper function allows you to do is build the scenario files or the simulation files that you need for your simulation. The wrapper function will then execute the simulation and also provide you with some ways to do some post-processing analysis. So our wrapper function, we had a couple different software packages within it in order to accomplish all of those tasks I just mentioned. So we first had to develop the scenario files. As you can see at the bottom of the screen, the simulation that ARL used, they built it utilizing Gamma. And Gamma takes XML files as their input files for the simulation. So the first task we had to do was figure out a way to develop the 12,000 scenario files that we needed. We tried R at first, the R programming language, but R is a little more trickier with developing the XML files the way we needed them to be. So we worked with another one of our TRAC centers, which is Fort Lee in Fort Lee, Virginia. Jonathan Shockley built us a Excel-based XML generation tool where we just had to put in the values that we needed to go in each one of the nodes of our XML file. So that gave us a way to develop the base XML file we needed. The next step we had to do was, in order to get statistical significance, we had to replicate each one of our individual rows 30 times. So this is where we utilized the R programming language. We were able to replicate each one of our rows 30 times. So that gives us that statistical significance. And what that ultimately does is give us 360,000 simulations to now run. So R allowed us to replicate the rows, and R also gave us a way to fill in the XML files with the appropriate values from the DOE matrix. After we did this, we had all of the necessary XML files with the 360,000 simulation runs built into them. The next step of the wrapper function was to now run or execute those simulations. I am located here at Monterey, California on a Naval Postgraduate School, and working with them, we have high performance computers, and we utilize their high performance computer in order to execute those 360 simulations. We do have in-house what we like to call supercomputers, but those computers do not have the capacity to run 360 simulations within a reasonable amount of time. It would have taken us roughly about, I think, right about 2 to 3 months to run all those simulations. And we just didn't have that time with our project. So the HPCs allowed us to run them more efficiently and made it more effective for us. We were able to reduce our time down to 6 days and 14 hours total computer run time in order to run our simulations. We did have to execute it in about 3 different batches because there was some simulations that didn't run, and that just was due to either memory allocation or just time allocation. But the HPC administrator, Mr. Hafferman, was able to oversee that portion of the project for us to ensure that all of our simulations ran, as well as compile the outputs of the simulation for us so that we can then inject them into our R program. And then the last step of the wrapper function is to do that post-processing analysis piece. So the wrapper function will take the results of the simulation, marry them back up to their respective simulation run so that we can have the results with the run. And then now we're able to conduct those post-processing analysis. And two things that we did was we did a regression analysis because we wanted to determine which combinations were, which interactions more or less between the factors was relevant, and also which of the factors was relevant. That was important because we wanted to know which of these factors affected the performance outputs of accuracy, noise, and duration. We wanted to know which one of our factors had the greatest impact on our factors. So we conducted a regression analysis for that. And then after that, we did a parametric analysis to determine the breakpoints for those factors, essentially the interactions of them. At which point did we stop increasing for accuracy, or at which point did we stop increasing for duration based off of the combination of UAVs and human operators in the simulation. So all of that was conducted in the post-processing phase or portion of the wrapper function. So now where we're at is where you see the gold star. We're in actually two different phases of the methodology. We're in phase 5 as well as phase 6. We've conducted the analysis, and we did provide the final outbrief to ARL, and they was very pleased with the results that we provided with them, and that there is going to be some additional follow-on work as the result of this work. We also developed the Shiny application for them. They liked the way that worked, how the senior leader can interact with it, and they can they can pick different constraints. They can say which roles they want to keep in the application, which roles they don't want to keep in the application. And the last step is to develop the report. We're writing a report as well as writing a paper. Dr. Human, who is the individual who created it, he wants to put it in a journal. So we're doing the paper as well as we'll present some of our findings at Gamma Days, which is a conference that the Gamma platform personnel host every year. If there's no questions, I'll move on. Okay. So what we're going to discuss now is a little more about the regression analysis that we conducted. As I mentioned before, we did our regression analysis because we wanted to determine factor importance. We wanted to know which of the factors could we ignore, which of the factors could we not ignore. We wanted to know which of the interactions of the factors was important, which interactions were not important. And we wanted to also know, the last thing we wanted to be able to determine was what is the relationship between the factors and the output. So what is the relationship between independent variables and dependent variables? These are all the things that we wanted the regression analyst to be able to answer for us. So we did the first phase. So our initial analysis told us that, one, all of our factors mattered, which is a good and a bad thing. Good thing, we didn't have to worry about eliminating them, and that's also the bad part too. And one of the reasons why all of our factors mattered is because we had so many observations. We had 360,000 observations. We did not average out our rows to get back to the 12,000 because conducting a regression analysis on average results is not going to really show you the true information. We had to conduct a regression analysis on the raw data. And then the next thing we learned is that our problem was nonlinear. And that was a good and bad thing. A good thing about it being nonlinear is that we can see that we can only look at the interactions. The bad thing was we wanted to know what was that relationship. We wanted to be able to have that predictive quality. We wanted to be able to say, if we add an extra operator, accuracy goes up by this much. Or if we add extra, say, quadcopters or flapping wings, duration or noise level will increase or decrease. We wanted to be able to say that. But since the problem is not linear, we couldn't. But we could use it in order to determine what those interactions look like. So that's what the regression analysis ultimately ended up doing for us, is showing us how those factors interact with us and how does that interaction affect the dependent variables, which is the the simulation outputs of accuracy, noise, and speed. So we did the regression analysis again. We utilized a couple different software packages in doing this. We used JUMP, JMP, and this software package allowed us to do the regression analysis and see instantly how those interactions graphically were being affected, how those interactions, affected the outputs graphically. Was able to see that instantaneous and a lot utilizing the JUMP software. So we wanted to be able to investigate that behavior a little more, or a little more in depth. So we then took those results from JUMP and imported them into R. And that was able to show us how those interactions between, say, 2 or 3 of the variables were affecting the accuracy, the noise, and even the duration of the simulation. So that's what we're now going to discuss. Anytime we conduct analysis, we always translate our numbers in our geek speak, so to speak, into visuals for our senior leaders, because they can take those visuals and show how things are changing, how if we add certain things that it either improve or it doesn't improve. They can utilize, excuse me again, I apologize for this. It takes our those results and it gives it in a very presentable format for our senior leaders to be able to understand what our numbers is telling us. So this is one of the visuals that I provided for ARL, and this shows you the parametric analysis for accuracy. And the two variables that we held constant were fixed wing at 6 and quadcopter at 3. We determined those by looking at the interactions between those two particular variables with accuracy to figure out what was the point at which they no longer improved. So that's the numbers we wanted to hold it at, because we know that is the highest point that they will ever get for a particular accuracy rating. In the particular graph you see, I have accuracy is on your left-hand side with the ranges of 75 to 100. We have the number of operators on your x-axis from 1 to 10. The arcs that you see in the graph represents the flapping wing UAVs, and they range from 1 through 10. I have highlighted on the graph 1 and 3 flapping wing, as well as the bottom half of the flapping wing, to show you that as the number of the flapping wing systems increase, the accuracy decrease. And you can see that starting at the very top here, this represents 1, all the way down to the last one, it represents 10. And you can see how if you are sitting on, or if you're at 3 operators, you start with an accuracy just below 95%. So we're probably around 92, 93%. But as you increase the number of flapping wings into the system, the accuracy of the operator begins to degrade. And this actually does make sense, because that means that there's more autonomous systems inside of the simulation. So the more systems you have, it's sending in more images for the operators to identify. And it's only 3 operators in the system. So by the time you get down to 10 flapping wings, you're actually at 19 autonomous systems in the simulation that is feeding images to the operator to accurately identify. And the inner workings of the simulation I'm vaguely familiar with, but I know Dr. Heumann put in the simulation, like fatigue factors in there. So the more information they do get fatigued. So they're just being overwhelmed with information. So that's just being reflected here on the graph for you. I also have the 90% line highlighted. So for example, if 90% was the accuracy rate that you wanted to achieve, you can see that at different points along the operator line, as you vary operator across, you can see how many autonomous systems in the simulation will be able, the operator will be able to stay at a 90% accuracy rate. And the break point for, at that point for 90% is 1, 2, 3, is 4, is 4 flapping wing. That is the break point for 3 operators. Anything over 4 flapping wing, 3 operators will not be able to maintain, say, that 90% accuracy rating. And you can see this breakpoint all the way across down to 5 operators. Now we're upwards of about 9 flapping wing into the system. So we have 18 autonomous systems in. So this just gives you an idea of at what point can I get the most accuracy from my operators. Like, what is the least number of autonomous systems do I need, and the least number of operators do I need to, say, reach a 90% accuracy rating. So these are the types of visuals that we can provide for our senior leaders to be able to translate all the analysis that we did on the backside into something useful for them to be able to then take from here and utilize and, say, maybe some later briefings, or use to develop some type of policies or programs or something along those lines, depending on what your project is relating to. So after I conducted this analysis, I then took this information and put it into what we call the multi-attribute decision-making optimization tool. So multi-attribute decision-making is just basically saying we have a lot of attributes that have, at some point, they probably do conflict with one another. So for this situation, if I want a good accuracy, I would say I need a lot of operators, but also having a lot of operators may require me to have more flapping wings, because you just don't want your operators, autonomous systems, because you don't want your operators sitting around. So you have to have a good balance of what you're requesting. So multi-attribute decision-making allows a senior leader to take all those different types of attributes and weigh them accordingly. And it provides a system to basically help with trade space, or to deal with that conflict resolution of your attributes. So as I mentioned before, the technique that we utilized was the simple additive weighting scheme. And simple additive weighting is also called the weighted summation, because the way it works is you rank all of your attributes, and then it takes those weights, multiply them across the rows, and it sums up the weights. And after it sums the weights, it ranks them. And then the rank with the highest is rank number 1, all the way down to whatever your largest alternative is, to 12. So we have a ranking from 1 to 12,000 in our simulation. And what it then returns back is, for our simulation, as you can see here in the results, it returns back the top 3 results. And these are all of the things that the senior leader can rank. They can rank the total number of UAVs in a simulation. They can rank the accuracy of the simulation. They can rank the duration. They can rank the noise, and they can also rank the total number of operators that they want to have in the simulation. So once they put that ranking there, they will then return these top 3 results. And as you can see, there are some trade-offs that is occurring. We can see that accuracy, even though rank number 3 has a 94% accuracy and has the same duration of 105, the noise level is lower, or the noise duration time frame is lower for the number 1 ranking. So with this type of scheme, accuracy must have been important, but noise must have been important as well. So there's a trade-off that's going to occur, and you got to, the inner workings of the simple additive weighting will help to deal with that conflict resolution right there. And this is how these are the results that you'll end up having as a result. And then another aspect of the application is that it allows the senior leader to do a results comparison. So this can be one particular set of weighted attributes. If the senior leaders say, you know what, I really want accuracy to be more important and then noise to not be as important. So they can then rank accuracy the same way, but then drop down the ranking of noise to see how does that affect the optimal combination that they'll receive at the end. So the app will has that as an option as well. So this overall tool is going to be useful for ARL. They'll be able to implement this and see how does the reconnaissance missions combinations changed based on how a senior leader is going to utilize their weighting schemes. And then the next steps for this for Dr. Human is that he wants this to be a part of, say, some type of war game scenario where the senior leader will utilize the simulation first to test out different platform combinations and number of human operators, figure out what that optimal number is, and then implement that information into the war game to see how the war game will play out based off of the simulation saying this is what the optimal information would be. So that concludes my brief. Are there any questions?
Hi, Major Fletcher. I just want to say thank you for presenting that. That was very interesting.
Thank you. I'm going to stop sharing my screen so I can get started for my second brief.
I was going to say thank you so much. We'll go ahead and take a 5-minute break, and we'll go ahead and start your next one at 11.
Okay.
Great. Thank you.
You're welcome.